Good morning, everyone. Okay, in previous session we observed that the lookup table implementation of different variable functions. Now, from this class onwards, we are going to develop VHDL programs for various combinational circuits. Okay, so first of all, coming to adders. Okay, so what for adders? To do the sum on binary numbers, the adders are preferred. Okay, under these adders we have half adder. Basically this is the basic building block in adders case. Okay, half adder. Okay, so in half adder case, what is half adder means? The half adder can add two bits and gives two outputs. One is sum and another one is carry. Okay, so let us see the truth table of half adder with two inputs x, y. Therefore, the different possibilities are 0, 0, 0, 1, 1, 0, 1, 1. Okay, and two outputs I said, one is sum output and another one is carry output. The sum outputs are getting like this. For 0, 0 inputs, the sum is 0, carry is 0. For 0, 1 input, sum is 1, carry is 0. For 1, 0 input, sum is 1, carry is 0. For 1, 1 combination, the sum value is 0, carry value is 1. So like that in DLD itself we prepared one truth table for the half adder case, isn't it? Now we realized the Boolean equation, or we derived Boolean equation for S and carry. Okay, observing this truth table. By observing this truth table, suppose if here S equal to S is we are getting like 0, 1, 1, 0 with the combinations of inputs like 0, 0, 0, 1, 1, 0, 1, 1. So that the x, y, s, if you observe the truth table between these three columns, it satisfies the truth table of two input XOR gate. So S is the XOR operation on the inputs x and y. Similarly, if you observe the carry column with input columns x and y, the truth table satisfying the AND gate truth table, AND gate. Okay, so that is the carry is the AND operation on the input variables x and y. So the sum equation is x XOR y, carry equation is xy. Okay, so by knowing the Boolean equations, the realization can be done. That is, the Boolean equations represents we require two gates. One is the XOR gate and another one is AND gate. The XOR gate is by using XOR gate you can get the sum result. Using AND gate you can get the carry result. Okay, so this is the realization of half adder. Now for this half adder, how to develop the VHDL program? Of course, in previous classes also I said how to write the VHDL program for the adders. Right? Half adder we have written, full adder we have written. Though I am going to show once again. Okay, that is whatever the program, first of all you need to open library IEEE followed by one package, that is standard logic 1164, that you have to open. After that, entity declaration. As per the reference book given, I am taking the same names here. Entity 1 bit half adder is port of two inputs, one is x in standard logic, another input is y in standard logic, two outputs s and carry co. Based on the previous diagram I am giving those names. And architecture body is architecture name is data flow of, entity name is 1 bit half adder is, then architecture begin. So here the model is data flow model. I said in the data flow model the statements are just signal assignment statements. Their syntax is like Boolean equation. Now what is the statement is for sum as per the Boolean equation, right? What is the Boolean equation for S? S equal to x XOR y, right? Similarly, now the statement is S less than equal to x, the operator XOR y. Similarly for carry, CO is the notation given in the declaration, less than equal X, logical AND operator Y, then end data flow. That is the architecture name, end architecture name. So this is the program for the half adder. Of course previous case also we have written, but though I am going to show once again. Okay, similarly for full adder case, this is the truth table and logic diagram. Okay, so from the truth table you can derive the Boolean equations. Of course here logic diagram also there. For Boolean equation, with the Boolean equation you can develop the program like this. This is the entity declaration and architecture body. So already from the truth table you know the sum equations. S is X XOR Y XOR Ci. It is the third input. Okay, X XOR Y XOR Ci, whereas carry is XY plus YCI, XCI plus YCI. Okay, so the implementation is very easy if you know the Boolean equations in the data flow style. Okay, so this is a half adder and full adder VHDL programs. Now coming to the another combination circuit. So like that I think you develop here I have shown only half adder and full adder. Okay, so now the assignment is like, just take the assignment, write a VHDL program for half subtractor, full subtractor, half subtractor and full subtractor. Okay, after that we can see ripple carry adder like that, ripple carry adder. Okay, so can you implement? Okay, definitely you can implement, no problem. Okay, here just data flow style I have shown. Okay, then coming to comparators. Okay, in comparator, simple comparator case, in simple comparator case, here the relation also represented. What is comparator? First of all, comparator is for comparing the numbers to know whether they are equal numbers or which number is greater and which number is less. Okay, so on 2-bit comparator, see 1-bit comparator or 1-bit comparator means it compares to 1 bits. It compares to 1 bits. So I said already the expected results are equal, greater than, less than. Okay, so the truth table is, so that the truth table part is in 1-bit comparator case, 1-bit comparator case compares two numbers, each number consists 1 bit. So x, y are the inputs with 1 bit. So power possibilities are 0 0 0 1 1 0 1 1 and 3 output bits. One is the greater than, x greater than y, and x equal to y and x less than y. I'll reference the x less than y. Okay, so based on this logic prepare the truth table first of all. So 0 0, first combination is x is 0, y. That means what? From this both are the equal inputs, therefore the expected output is logic 1 under equal, whereas other two cases we may get the 0. Okay, then coming to second combination, x is 0, y is 1. Since the bits are not equal, therefore the e value is 0. That is equal output is 0. Okay, then coming to other outputs, greater than, less than. Okay, x greater than y. Now x value is 0, y value is 1. Is it x greater than y? No. So the greater than output also 0. Hence the third output, that is x less than y, is the right answer. So here x less than y output gives the logic 1. Clear? Similarly, if you go for another combination 1 0, x is 1, y is 0, means these two are the not equal inputs. So expected output under equal is 0 and greater than y, x greater than y. What about this x greater than y? Sure, right, it is a right answer because x is 1, y is 0. So x greater than y is 1, whereas x less than y is 0. Okay, and coming to last one, 1 1 case, last combination 1 1 case, since both the inputs are 1 1, the equal output gives the logic 1, whereas the other two outputs gives logic 0. Okay, so like that the truth table is developed. After that, comparing the input combinations and output results, what is the expected equation, what is the Boolean equation for G, E and L? So for G, if you observe here, the equation is x y bar. X y bar is the Boolean equation for G, whereas for E it is the x nor y, or complement of x or y, complement of x or y. Okay, whereas L is obtained by the equation x bar y. So let us observe those, the Boolean equation for G, E, L like this. For G, this is the Boolean equation. For E, this is the Boolean equation. For L, this is the Boolean equation. Now once you know this, the realization is very easy. Okay, here we need to have y complement through NOT gate, x complement to NOT gate. After that, the product is by AND gate, L product also by AND gate. This is the XOR operator, so an XOR gate we required. Okay, after XOR operation on x and y, since the E is complement of x XOR y, therefore the output of XOR gate will be complemented using one NOT gate. Then the NOT gate output is treated as the equal output. Okay, so this is the realization. Okay, development of truth table, preparing Boolean equations, and realization using logic gates. Now for this, after that it is better to develop the VHDL program. I think now Boolean equations are available, means you can easily write the program in the data flow mode. So as usual, first of all you have to write the library IEEE, followed by opening one package, then entity declaration. As per the number of inputs and outputs, the entity has to be declared. In the entity you have to show two inputs, x is one input, y is another input, three outputs, G is one output, L is one output, E is the another output, not EQ. Okay, E is the another output. Based on the diagram I said, you can place EQ also, no problem. So in the entity declaration, what are the input ports, how many are the input ports, what are those data types, all mentioned here. Then coming to architecture body, it start with the word architecture name of entity name is begin. Since it is a data flow style, Boolean equations directly you can take. So the for greater than output, the equation is G less than or equal to x AND operator followed by NOT operator, then y. Equal output we may get like NOT operator of x XOR y. Okay, as per equation I am writing. Okay, so L is not x and y. Okay, and data flow. Clear? So these are the equations. The same thing I am implementing. Bar means bar is implemented by, that is complemented through NOT gate. Dot operation by AND gates. XOR operation by XOR gates. Right? So the VHDL program for the comparator is like this. So in the next class you can see this is the program what n-bit comparator also written. Okay, n-bit comparator also written, so that you can see in the next class. Okay, so after n-bit comparator we have the decoder, right? So I think you practice up to this. Okay, so write the program for half subtractor, full subtractor, and also prepare the comparator program. Of course I have given for 1-bit comparator, you prepare 2-bit comparator, 3-bit comparator, like that. But in next class I will discuss with you about the n-bit comparator, right?